Okay, in this video we're going to work the 2017 AP Calculus Official Practice Exam number 6. Alright, so number 6 starts with a problem that I do think is fair game for the 2020 tests, and it involves related rates. So I'll remind you how to work a related rate problem in this one. And I think it's a problem that's easy enough that I do think it could definitely be on, one like this could be on the exam. So reading part A, it says for 0 to 6 seconds, a screensaver on a computer screen shows two circles that start as dots and expand outward. At the instant the first circle has a radius of 9 centimeters, the radius is increasing at a rate of 3/2 centimeters per second. Find the rate at which the area of the circle is changing at that instant. Okay, we want to find a rate at which the area of the circle. And we got to indicate units. You know you want to get those units right. So with related rates, we have a process. First of all, we want to write out what we want. We want the rate of change of area. What do we know? Well, it tells us that the radius is increasing. So that's dr dt is equal to 3/2. And then we have to relate what we want to what we know. Well, what's the equation for the area of a circle? We got to have that because we're relating area to radius, and that's area is equal to pi r squared. What do we have to do to that pi r squared? We have to differentiate with respect to time for related rates. So that would be dA dt is equal to 2 pi r. Bring that 2 out front. Don't forget the derivative of r dr dt. Otherwise, you wouldn't be able to plug that in. Okay, so that's going to be 2 pi. Well, what is r? We don't even have to figure this out. They just told us, so that certainly makes it easy. That's 9. What is dr dt? 3/2. So that's, the 2's cancel. 9 times 3 is 27. 27 pi. Area is going to be squared, right? The unit squared. So it's area per unit time. So centimeters squared. Very important to get the unit right. Per second. Okay, that is not bad. You can do that. I really think that's the level of problems that we're looking at. We'll see. No one really knows. Okay, going to erase that. We'll try part B. So part B says that the radius of the first circle is modeled by W of t is equal to 12 minus 12e to the minus 0.5 t from 0 to 6 seconds. At what time t is the radius of the circle increasing at a rate of 3 centimeters per second? Well, if something's increasing at a rate, that means anytime you're looking for a rate, you're looking for the derivative. Okay, so what we're trying to see, where does W of t, what time t is it increasing at a rate of 3 centimeters per second? So we want to know, where does W prime of t, the derivative of that gives us the rate, equal to 3. Okay, no problem. We can get W prime of t. The derivative of 12 is 0. Okay, so that's going to be minus 12e to the minus 0.5 t times the derivative of the blob, negative 0.5 t. So times negative 0.5. So that's going to equal negative 12 times negative 0.5 would be positive 6 e to the minus 0.5 t. We want to solve for t. What time t does that rate equal to 3? So divide both sides by 6. You'd have e to the minus 0.5 t is equal to 3 over 6, or 1/2. Okay, how do I get how do I solve for t? What do we do to both sides? I'll let you tell me. All right, you got it? We take the natural log. Natural log of e to the minus 0.5t is equal to the natural log of 1/2. It's like those half-life problems, right? So now we can bring that minus 0.5t out front times the natural log of e, that's just 1, is equal to natural log of 1/2. So minus 0.5t is equal to the natural log of 1/2. So t is equal to the natural log of 1/2 over negative 0.5. I believe that you could just circle that, because you're not supposed to have to use a calculator. You can just circle that as your answer. Natural log of 1/2 is negative, so you're not going to get a negative time here. You do get to, you know, they say have a cheap calculator ready, so like this. So we can do, what is the natural log of 1/2? Natural log of 0.5 is negative 0.693, if you're just dying to know, over negative 0.5. We do want to put the units, so divided by negative 0.5 is 1.386 seconds. You do not have to take, if you have the time to do that, that's cool. I just wanted to show you that it's not a negative time, since if you had physics class, you know you can't have a negative time. I just wanted to make sure that you knew that it wasn't. But you could, but now don't forget you've got to put the unit. You could circle that also, and that might be the wise thing to do. Okay, so pause the video if you need, and we'll move on to part C, and then we'll be done with this video. Okay, part C. Okay, it says, reading through that, a model for the radius of the second circle is given by the function f of t measured in centimeters, t is in seconds. The rate of change is f prime of t is t squared minus 4t plus 4. Based on this model, how many centimeters does the radius of the circle increase from time 0 to 3? All right, I'm not totally sure if you would get a problem like this or not. I'm going to go ahead and work it, because I do believe it's probably one that you could get. So f prime of t, and it's not hard also, is t squared minus 4t plus 4. What it wants to know is how many centimeters does the radius increase. So we could get that from 0 to 3 of f of t dt. Or we would get f prime of t, excuse me. If we integrate that from 0 to 3, we would get the original function f of t, right? From 0 to 3. So to integrate f prime of t, okay, so that's 0 to 3 of t squared minus 4t plus 4. That'd be 1/3 t cubed minus 2t squared plus 4t, and we have to evaluate that from 0 to 3. So that's 1/3 times 3 cubed minus 2 times 3 squared plus 4 times 3, and then we get to plug a 0 into all that, so yay. 3 cubed, that's not 9, that is 27. 27 over 3 is 9. 2 times 9, 9 minus 18 plus 12. All right, so that's negative 9 plus 12, which is 3. Okay, what is the unit? It says how many centimeters. Don't forget the units. You don't want to have them ding you on little things like that. So 3 centimeters. So hey, that's a good problem. We can totally handle problem number 6. And it's this level of problem that I think we're going to be looking at for the 2020 test. I don't know if you'll get exactly, you might not have a related rates problem on the 2020 test, but it's certainly, this is the level of difficulty I'm kind of expecting. All right, I will talk to you next video.